So example number 5, they want us to use 4 rectangles to find 2 approximations of the area of the region lying under the graph of f of x equals 6 minus x squared and the x-axis between 0 and 2. So we're going to do right endpoints and left endpoints with 4 rectangles, and that's going to give us our 2 approximations. So I'd like to first go ahead and sketch these, and then we'll start with right endpoints first. So first, let's figure out delta x. And you can see it from the graph that we have a distance of a half. But if we were to do it in general, right, we're talking about widths, right? That's our delta x right there. So we have delta x is equal to b minus a over n. Well, we have b is 2, a is 0, right? We're going from 0 to 2, right? Here's 0. And we have 4 rectangles, if I'm not mistaken, is what the plan is. And so that ends up being a half. So that is our delta x. And so that's going to be the width of each of our rectangles. And we're going to start off doing right endpoints. So we have x's doing what? Well, let's take a look. If we look at our first rectangle, the right endpoint of our first interval is going to be at a half. We bring that straight up to our function. And there is our first rectangle. Okay, so what did we do? We got at this x value by starting at 0 and adding delta x once. Okay, the next right endpoint is going to be here at 1. And how did we get that x value? We started at 0, I should say, and we added 1/2, which is delta x, times 2, right? We started at 0. If we add 2 times a half, we get to 1. The next right endpoint is going to be right here. And you might be seeing a pattern already. We're starting at 0. We're adding delta x, which is a half, 3 times. Then we go 1 more here. To get to that guy, we are starting at 0 and adding 1/2 4 times. And the numbers you see, 1, 2, 3, 4, right? These numbers in yellow are simply counting which rectangle we're on. So that's what our I is doing. I is going 1, 2, 3, 4. So we can write this in general. X is equal to, well, the 0 is not doing anything. So I'm just going to write 1/2 I, where I equals 1, 2, 3, 4. So hopefully that makes sense. If not, pause, rewind, rewatch that part, because that tends to be one of the trickiest things we have here. So we'll go ahead and use that. So we have the widths of the rectangles we know to be a half already. So now we need the height of each rectangle, right? Height of, we'll say, ith rectangle. That's going to be what? Well, let's think about this for a second. If we start with our first rectangle, right? We're trying to get this area right here. We want the height here at a half going up to the function, right? Well, what is that orange length? It's simply the value of the function at a half, right? It's going to be the height up to the function at a half. In other words, f of 1/2. So we can write that the height of our rectangles is going to be f of our right endpoints. Right? Same thing with this next one. We're getting the height for this rectangle that I'm coloring in now at 1. F of 1 is the height of that second rectangle. F of 3/2 is the height of the third one. F of 2 is the height of the last one. So in this case, that's going to be F of 1/2 I, our right endpoints. And so now we want to get the sum of the areas of our rectangles. So let's write that up. Sum of areas of rectangles. Well, we're going to add 4 rectangles, and they're all going to have the same form. So I'm going to have the height, F of 1/2 I, times the width, which is 1/2, right? This is height, that is width. We multiply those. When I equals 1, we'll have the area of the first rectangle. When I equals 2, we'll have the area of the second rectangle. When I is 3, we'll have the area of the third rectangle, and so on and so forth. And then we want to add them up. So we're going to put a sum I equals 1 to 4. So we need to simplify this into an expression that's easy for us to work with. So here we go. We're going to have the sum I equals 1 to 4. We are going to plug in 1/2 I right there into our function, right? That's how we get the height of each rectangle. In other words, we're going to take 6 minus x squared. Instead of x, we're going to plug in 1/2 I. So we're going to have 6 minus 1/2 I squared. Okay, this isn't any more complicated than taking an x value and plugging it into your function to get the height of that rectangle. And from there, we have to multiply by 1/2 because that's the width. So again, this is the height, this is the width of our ith rectangle, right? Of the ith rectangle. Then we can do it for I equals 1, I equals 2, and so on and so forth. So we're going to continue simplifying this. This is equal to the sum I equals 1 to 4. And we're going to get 6 minus 1/4 I squared, all of that times 1/2. That will become the sum I equals 1 to 4. Distributing the half, we get 3 minus 1/8 I squared, like that. Now I'm going to split it up into 2 summations. So we have the sum I equals 1 to 4 of 3 minus, I'm going to factor out the 1/8 and get the sum I equals 1 to 4 of I squared. And now we're going to get to use our formulas for summation. So you'll notice with the first summation here in yellow, we've got the sum of a constant. So we're going to use the yellow formula there. And the second one, we're taking the sum of the I squared. So we're going to use the green one. So let's see what that turns into. That's going to give us the constant 3 times the upper bound of summation, which is 4. So that's going to be 3 times 4 minus 1/8 times our upper bound of summation n, in this case is 4, right? The number of rectangles is 4. So we're going to take the green formula there in the upper right-hand corner of your screen, and we're going to put 4 in for every n. So we're going to have 4 times 4 plus 1 times 2 times 4 plus 1 all over 6. Simplifying that, we have 12 minus, we have a 1/8 here. We have times 4 times 5 times 9 over 6. We can cancel a little bit. Here we get a 3, here we get a 2. We can cancel here, we get a 4. So now we have 12 minus, what is that, 15 over 4. which is going to give us, well, it's going to give us exactly 8.25. So there is our first approximation using right endpoints. That 8.25 is the sum of the areas of those 4 green rectangles that you see, and that is an approximation of the area under the curve. Of course, it's less than the area under the curve because we have those white spaces there, right? These guys here, and this one, and this one, and this one, that we have these little gaps that are unaccounted for. But as we saw earlier, we're going to take care of those by taking a limit as the number of rectangles goes to infinity. So now let's go ahead and look at left endpoints. So what are the left endpoints going to look like? Well, let's go ahead and start here. If we look at our first subinterval, we're looking at the left endpoint, which is going to be right there on the y-axis, going up to there. We're getting the height of our rectangle like that. And so we do it again, getting the height of the next rectangle at 1/2. And the next one at 1. Then at 3/2. And there we have our rectangles we get from left endpoints. Okay, now let's think about how we're going to actually find these left endpoints. So we want left endpoints that are going to start right there. And we have to include I because I is counting our rectangles. So if we start with an x value of 0, right? And then we want to add the width, which is 1/2, 0 times. But we want this to be for our first rectangle, so we want I to be 1. So the way we can take I equaling 1 and change it to 0 is subtract 1, right? In other words, I minus 1, right? So actually, let's do this kind of like I did before. Watch. This first left endpoint is going to be x equals 0 plus 1/2 times 0, right? No delta x's, no widths. This one is going to be x equals 0 plus 1/2 times 1. And this one over here is going to be x equals 0 plus 1/2 times 2, and so on and so forth. We get to do it for 3 right there. That is 4 rectangles, right? So what are these? Well, this one right here in yellow is for our first rectangle. So if I represents our first rectangle, we put I minus 1, and the first rectangle would be 1 minus 1 equals 0. And this next one, we're going to put I minus 1, and we plug in 2 for our second rectangle, we get the 1 in yellow. For the next one, we put in 3 for I into this I minus 1, and that will give us a 2, and so on and so forth. So each one of these is an I minus 1, right? The fourth rectangle is what we have here, and we get it by taking 1/2 times 3, which is 1 less than 4. So the way we write that in general is we're going to have our left endpoints at x equals 0, right? Starting at 0, and then add on to that 1/2 times I minus 1, where I equals 1, 2, 3, 4. And if you don't totally see that, that's okay. Pause the video and plug these in. Plug in 1 there. You're going to start at 0. Plug in 2 there. You're going to start, you're going to then have 1/2. You're going to have 1/2, and then plug in 3 and 4 and see what it does. It should give you each of these left endpoints that we've just written up here. Okay, so now we want to get the height of our ith rectangle. So height of ith rectangle is simply going to be f of the left endpoint, right? And that for us is going to be f of 1/2 I minus 1, or you can write I minus 1 over 2 like that. So that gives us the height of each of our rectangles. And so now we want the sum of the areas, right? So we want the sum of areas of rectangles I equals 1 to 4 of the height of the rectangle, f of I minus 1 over 2 times the width, which is 1/2. So from there, we're going to look back at our function way up here, and we're actually going to plug in I minus 1 over 2 to get the heights of each of our rectangles. And so that's going to look something like the sum I equals 1 to 4 of 6 minus I minus 1 over 2 squared, right? I took that I minus 1 over 2 and I plugged it up here into my function for x, and all of that is going to multiply 1/2. And so now we've just got to simplify this down and use our summation formulas to evaluate, and then we'll be in good shape. So what do we get? We have the sum I equals 1 to 4. We have 6 minus, well, if we square this, we're going to get I squared minus 2I plus 1 over 4. And all of that is being multiplied by 1/2. So here we have the sum I equals 1 to 4. If I distribute the 1/2, I'll have a 3 here minus I squared minus 2I plus 1 over 8. Like that. Let's go ahead and keep simplifying. We have the sum I equals 1 to 4. I'm going to split up this guy here into 3 separate fractions, distributing the negative sign. So watch carefully. We've got our 3. Let's write it like this. Let's write minus 1/8 I squared. Then distributing the negative, we're going to have positive 2 over 8 is 1/4 I. And then distributing the negative, we're going to have a minus 1 over 8, like that. Simplifying just a little bit further, I've got a 3 in front, which is the same as 24 over 8. And if we subtract 1 over 8, we're going to get 23 over 8. So let's go ahead and write the minus 1/8 I squared plus 1/4 I and plus 23 over 8, like that. So if we can go ahead and evaluate this, we're done. Well, there's good news, because if you look at what you see right here, and then we scroll up to an example we did earlier, right here, it's this, isn't it? That's exactly what we just came up with using left endpoints on our function with 4 rectangles. Great, we've done this work. We know what this is. The result of this thing is 10.25. So which example was that? That was example 3. So I'll just write down here equals 10.25 from example 3. And so what we have is we've just found in purple the sum of the areas of these rectangles here that are bleeding over our curve there. but the actual area under the curve is actually somewhere in between these two, right? What we have is the, I'll just say actual area under curve between 0 and 2 and above the x-axis is going to be greater than 8.25 because the green has all those gaps underneath the curve, but less than 10.25 because the purple has all those bits of rectangles that are going above the curve. And so we know our actual areas between those two. And again, as we've already talked about several times, as we have more and more rectangles, the areas of these sums of areas of rectangles are going to get closer and closer to the actual area under the curve. And what you see with more and more rectangles is this number gets bigger and bigger, approaching some number. This number gets smaller and smaller, approaching the same number. They're kind of squeezing in on the actual area under the curve. So what you'll notice is that we have what's called an upper sum and a lower sum. So this picture here represents a lower sum because it's a sum of areas of rectangles that's less than the actual area under the curve. And this one over here is what we call an upper sum, right? The sum of those areas are going to be more than the area under the curve. And so this next bit here in the notes is just kind of going through this concept of upper sums and lower sums and getting a kind of a generalized approach for using these approximations by rectangles. So we have this function f is continuous, and we're using n rectangles, just like we've discussed, over the interval AB. Then the width of the rectangle is, PDF conversion got rid of my delta and turned it into a capital D. So go ahead and make that a delta. Delta x, here I'll make the x dark too, so hopefully that's obvious what's going on. Delta x is b minus a over n, as we've already discussed. B minus a is the distance for the entire interval. We divide it into n parts, right? N subintervals, and that gives us the width of each one. Since f is continuous, we have the extreme value theorem, which says we have a maximum and a minimum on each one of those intervals. Okay, let me just quickly show you how we have that here. If we look at the second interval, this is the max on that second interval, and this is the min on that second interval. Okay, on every one of these subintervals, we always have a max and a min. Okay. And so this height here is going to be f of, using the notation I'm about to show you, capital M sub I, meaning this is capital M, the x sub I, the x value where we get the maximum. And this one's going to be little m sub I. So this height would be f of little m sub I. And the idea here is that because we have a minimum value and a maximum value on each interval, subinterval, we can get the lower sum by taking the minimum values on each of our subintervals times the width, right? This is again just height times width. And because we're using the minimum values on each of our subintervals, we're getting the lower sum. And over here, we're using our maximum value on the subinterval times the width, and that's giving us our upper sum. And so that's the idea with upper sum and lower sum. Now, as we mentioned in the previous example, if we take the limit, well, first of all, notice right here, we have a lower sum because we have little m sub I. And here we have an upper sum. But as we take the limit of these guys as n approaches infinity, it turns out that these two values are approaching the same thing, right? These two limits are equal to each other. And so therefore, and that is the area under the curve that we're trying to find. So this goes into a lot more detail in more advanced calculus classes, but that's the idea of what we're doing here to find the area under the curve.
And next time in class,
we're going to go through and do that entire process with example 5.